Okay, so again, I'm Pfaff, and I'm a math professor at Queen's University in Kingston, Ontario. And I want to talk a little bit about one of the main methods of proof that we use, which is proof by contradiction. So here's kind of the method, kind of broken down for proving a statement P by proof by contradiction. Okay, and then we're gonna, and I wanna note the fact that for us, so P bar will denote the negation of P. So we've negated the statement, and I made a video, a lecture video, on how to negate the quantifiers part. One also needs to know how to negate the and or parts, but that will be another video. Okay, so suppose for the sake of contradiction would be, so the first line that I always want to see out of my students is I want them to indicate what method of proof they're using, but there's kind of a way to do it so that you're both letting us know what it is and actually kind of setting up what you're doing properly. Okay? So suppose for the sake of contradiction, and then you negate the statement. So there's a lot that you've kind of put into that sentence. You've told us what kind of proof you're doing. It's for the sake of contradiction. Okay, so this is a proof by contradiction. You've also told us what you're supposing and making it clear that this is something that you're only supposing for the sake of contradiction and you don't believe to be true. Okay, so it's got a very clear way to start one of these proofs. Okay, now we're going to use the assumption of, so we're going to use this assumption. So we've assumed or supposed this negated statement, and now we're going to use that to prove something that we know is false. Okay? So use the assumption of this negated statement to prove something known false. And this is like the meat of the proof. This is where there's a lot of work. The first is just kind of setting the reader up to understand what you're doing. This is really the meat of the proof. And then another piece of it that I think is important is you need to let us know what the contradiction is, like what you're contradicting with. So this is another kind of clarity piece of it. And so you can write, since blank contradicts. And it's usually good to even be more specific than this. I'm going to say P bar, but I'm going to actually kind of emphasize here. The more specific is even better. P must hold. Okay, and I want to make a remark on this. So this is going to be the method, and I'm going to show you an example of this. Before I show you an example of this, why does this logically work? So we're going to use something called modus tollens, and I'm sure I'm mispronouncing that. So proof by contradiction uses modus tollens. I.e., if we know P implies Q is true and can conclude that Q is false, then we can conclude that P is also false. Okay? And P implies Q is logically equivalent to this. Okay? So this is actually also, this is kind of a modified version of proof by contrapositive, right? They are related to each other, and a lot of times students kind of have troubles differentiating, and they are related, and sometimes you're actually just proving the contrapositive when you prove this, but sometimes more, it's more general in some sense, that sometimes more general things are going on. Okay. So I'm going to go through an example. So I'm actually going to erase the part where I talked about modus tollens, and a benefit of videos is you can pause if you need to. Okay, so claim so the difference of any rational number and irrational number is irrational. Okay, so proof. So this is where we're going to do part one. So suppose, for the sake of contradiction, that there exists so we have a rational number and an irrational number. So that now we want to take their difference and get something rational. Okay? So I negated here the conclusion, okay, that x minus y was going to be irrational. I negated it to say that x minus y is rational. Okay, so this part is my 1. Okay. Now this is kind of this meat of the proof, where again it helps to write things out using the definition. So by the definition of a rational number, there exists AC in the integers and BD in the natural numbers, and here I'm using the American natural numbers, or we do not include 0, so that I know that in some countries you include 0. So that x minus y, equals C over D, okay? So I'm changing both my x to be rational and the difference to be rational. Okay. Oh, and so that, I see. I actually wanted to, I want to start with, so I'm missing something in here. X equals A over B, and x minus y equals C over D. Now I've switched them both to be in their generic form. Okay, so this is just the part where I switch things to be in a general form using the definition. Okay, and now I want to actually, this is where I kind of manipulate things to get what I want. Okay, so, which is a contradiction. So here we go. By substituting x equals a over b, into x minus y equals c over d, we obtain a over b minus y equals c over d, and hence that y is going to equal AD minus BC divided by BD. Okay. So now I have to actually kind of reach a contradiction. Well, you can imagine the contradiction. So y is supposed to be an irrational number. So I just need to show that y is rational. Okay. So since A, B, C, D are in integers, and B, D are in the natural numbers, and the integers are closed under addition and multiplication and taking of inverses to handle the subtraction part. We know we know that AD minus BC is an integer. And we know that this product right here, we need that this is an integer and this is a natural number, and we know that this is a natural number because the natural numbers are closed under multiplication. So, and here's our contradiction. So y is a rational number, contradicting that we say was irrational. Okay, so it's really important that you actually tell us what you're contradicting. Okay? So this was the second part to this. So now we're just left with the third part. Okay? Which is really just saying, well, we reached a contradiction. That's what we want to be true is true. Hence, the difference of an irrational number and irrational number is irrational as desired. Okay, and there's barely room, but we stick in a QED. Okay, so this is kind of our last part. A little bit at the end there too. Okay, so we started out with our supposed for the sake of contradiction. We said what that statement was, and see the key part in here is that we negated, so instead of the difference being irrational, we said it's going to be rational. Okay, and then we went through and we kind of turned things in using the definitions into something we can work with, like in a generic form. You've seen this in a number of proofs. That's kind of how that works, often. And then by substituting, so then we actually kind of manipulate this. We substitute x equals a over b into here. We do some manipulating and we're like, oh wait, y looks like this, but this is in the integers and this is in the natural numbers, so this is in the rationals. And then we say, wait 1 second, perfect. Y was not supposed to be in the rational numbers, it was supposed to be irrational. And then we're careful to say what our contradiction is with. So we said, we've concluded that y is rational, but y was supposed to be irrational, right? we were very explicit about what our contradiction was, so then we could say, oh, great, so now our statement is true. So that's kind of how a proof by contradiction works.